Hi class, so this lecture is the first lecture in chapter 14. So in chapter 14, I've split it into 5 lectures. If you look on the schedule, we're not going to do every section in chapter 14, but we're going to do 5 of them. And we have 5, maybe a little more, six or 7 worksheets to do in this chapter. And so this chapter 14, is on acids and bases. It's an extension of equilibrium reactions, and acids and bases have their own particular chemistry, and most of them are equilibrium chemical reactions. And so it follows chapter 13 where we learn about equilibria, chemical equilibria. So let's get started. This lecture is going to be on chapter 14.1, and it's about definitions. Some of the definitions that have been made for acids and bases. So there's several ways to define acids and bases. So we're going to learn 2 of them today. So let me go to the screen share, and I'll find the PowerPoint. Here's the PowerPoint. And let me change to my camera, so that as soon as the PowerPoint's over, we'll do the spreadsheet. So chapter 14, some of the learning objectives as we work through this chapter: to know the definitions of acids and bases. Number 2, how acid concentration and acid strength and acidity are related. So these are kind of some of the new terms we will learn as we define acids and bases. And there are some acid concentration is really important, so we'll learn how to calculate that. Understand the factors affecting acid strength. So why are the acids, what kind of factors determine what acids are strong, what acids are weak? Be able to use and learn interconverted scales of acidity. Actually, that kind of number 4 should be moved up to number 2. We're going to apply equilibrium calculations to strong and weak acid solutions, and how equilibrium system offer solutions pH, and learn to understand the process and calculations associated with acid-base titrations. So we'll talk about titrations in the end. You're going to do a titration in your lab, I'm sure. Okay, let's get into chapter 14.1. It's about the definition, how we define acids. So the title of it, Bronsted Lowry acids and bases. That's what most of the chapter is, but we're going to start off by some other more basic definitions. So we're going to learn both the Arrhenius and the Bronsted Lowry definitions of acids and bases. Like I said, the focus will be on the Bronsted Lowry definition. We will be able to identify Bronsted Lowry acids and bases, and also what are called conjugate acids and bases in the chemical equation. Let's start off here. So first with Arrhenius acids and bases. So an Arrhenius acid is something that donates a proton, which is a hydrogen ion, in water. So we've all learned we've used these before in chemistry. So the common Arrhenius acids are hydrochloric acid, sulfuric acid, any of these compounds named as acids are compounds that donate a hydrogen proton in water. Now, it doesn't have to be in water, but that's what our study is going to be. We're going to mainly concentrate and focus our study on the acid-base chemistry in water. And what's an Arrhenius base? It's a substance that produces a hydroxide ion in water. So this would be like sodium hydroxide, potassium hydroxide. So compounds that have hydroxide in their name is an Arrhenius base. And so an acid solution, the substance is an acid typically, you can tell from the formula because the formula starts with an H. So a generic way to write acids is just HA. My A, where the H is the proton that's coming off. Let me get fancy here. Let me change the color of the pen. So that's, oops, back up, come on. This is the proton that comes off right here. There can be other hydrogens in the formula, but the one that dissociates or comes away from the other part, the anion, an anion is left behind usually. Not necessarily. We'll look at different formulas, but when that H comes off, that makes it an acid. And so this H is written first in the formula. So if you see a formula of something with H in front, at most of the time, 99% of the time, indicates it's an acid. Other compounds have the H's following some other element. Those are not acids. So a base is a hydroxide substance. So down here I have sodium hydroxide. And the most common Arrhenius bases are the alkali metal hydroxides and alkaline earth hydroxides. And this is the most formula, kind of the most specific definition of an acid bases. As we cover talk about some of the other definitions, they get more broad and include more and more compounds. So the alkaline metals and alkaline earth metals that have this, there's a group 1 and group 2 elements. Hydroxides are the Arrhenius acid bases. Now the way these work is that we say that acids ionize. So acids are molecular substances. So HCl actually is a gas. So when you put it in water, this bond between the hydrogen and chlorine is very weak. The hydrogen comes off as a hydrogen ion, and the chlorine stays behind as a chloride ion. So we say that acids ionize in water. Bases are ionic. So what happens when you put those in water, they dissociate. The positive ion and negative ion come apart. Okay, so so we say that bases, hydroxide bases dissociate, acids ionize. We're not going to spend too much time on Arrhenius acids and bases because we're going to go on to Bronsted Lowry acids and bases. And this is a much broader definition, but it includes Arrhenius acids and bases as a subset. So what's a Bronsted Lowry acid? It's something that donates a proton. It sort of sounds like an Arrhenius acid, and it is. What is hugely different is that a Bronsted Lowry base is something that's a proton acceptor. And so you can see this is a case, you can't, in the case of talking about Bronsted Lowry acids and bases, they go together. If the substance loses a hydrogen ion, well, something else has to accept the hydrogen ion. So in any chemical reaction involving a Bronsted Lowry acid, there has to be a Bronsted Lowry base because the hydrogen ion has to go someplace. So the hydrogen ion from the acid goes to a base, which is the acceptor. Now they're also in an equilibrium involving a Bronsted Lowry acid and base. There's also a conjugate acid and a conjugate base. Those appear on the product side. So the substance is an acid that donates the hydrogen ion. What's left over becomes a conjugate base. So if we look back here at HA, if this is the acid at the top right here of this slide, When we lose that proton, what's left over is an A minus. The A minus is called the conjugate base in the Bronsted-Lowry definition of acids and bases. Similarly, when a base accepts a proton, it becomes a conjugate acid. There are lots of examples of that on the worksheet that we're going to do. Lastly, if we're in water, when the substance loses a hydrogen ion, it becomes a hydronium ion, H3O+. So the hydrogen ion is almost, it's a hydrogen nucleus, right? The hydrogen atom is just has one electron and one proton. So if you take away that electron, you end up with a hydrogen ion, which we call some cases a proton, or hydrogen is only a nucleus with a proton in it. Well, that's a really highly energetic species. Doesn't like to be like that, so it's a proton without its electron, makes it a hydrogen ion. It's looking for electrons. It doesn't have an electron. It lost its only electron, so it's really looking for an electron. So if you're in water, the oxygen atom of water has some extra electrons. So that hydrogen ion latches onto the water molecule and it becomes a hydronium ion. So H3O+ is what we're going to talk about a lot as we go through this chapter. So that hydronium ion is really important, so don't forget that. So how does the Bronsted-Lowry acids and bases work? Well, on the first top of this slide, we have HCl in water. Well, the HCl we know is an acid, so the arrow shows that the hydrogen ion is leaving the HCl and latching onto the water molecule. When it does that, it becomes a hydronium ion and leaves behind chloride. And so here's the chloride there, with the arrow to the chloride. So the substance that's the acid has lost the hydrogen ion. The substance that is the base, that's labeled here, has accepted the hydrogen ion. So in this case, water is a base. Now, under the Arrhenius definition, water is not a base because it doesn't produce hydroxide. But in the Bronsted-Lowry definition, water accepts the hydrogen ion, so it's a base. What's left over from the acid is the chloride. So this is called the conjugate base. So the acid becomes a conjugate base, and I'll abbreviate that with the CB. So the acid became a conjugate base, and the water molecule, which now has picked up the proton, becomes a conjugate acid. So I'll write a Ca there. So the water molecule is the conjugate acid. So these terms, conjugate base, conjugate acid, only apply to substances on the product side of the reaction arrow. Here's another example of an acid-base reaction in the lower part of this slide. Again, we're using HCl, and this time we have ammonia as a base. Ammonia is the proton acceptor. So ammonia is the base. So one of the goals is to be able to identify in a chemical reaction, first of all, be able to tell if it's an acid-base reaction. And acid-base reactions are proton transfer reactions. So if you look at a reaction, if you're looking at a reaction and a hydrogen ion transfers from one molecule to another, that's an acid-base reaction. In this case, we can identify the HCl as the acid because it donates the hydrogen ion, and the ammonia as the base because it accepts the hydrogen ion. On the product side, the ammonium ion then becomes the conjugate acid. And the chloride, or the chloride ion becomes a conjugate base. So that's, as you finish chapter section 14.1, that's the goal, be able to identify an acid-base reaction, be able to identify which substance is the acid, which is a base, and be able to label the conjugate acid and conjugate base that results. This shows another example. At the top, we have hydrofluoric acid and water. The hydrofluoric acid gives up the hydrogen ion to water. So the HF is the acid. F minus becomes a conjugate base. And water is the base. And H3O plus, the hydronium ion, is the conjugate acid. Now this should say C. This is where it should be the conjugate acid, conjugate base. They're labeled on the bottom correctly. But the pair, the water, the H2O, and the hydronium ion is called a conjugate pair. So that's the other goal, is to be able to recognize conjugate pairs. Now for something to be an acid, it has to have a hydrogen atom, right? You can't lose an H plus if you don't have a hydrogen atom. For something to be a base, it just has to have a lone pair of electrons to be able to accept that hydrogen atom. So there are two conjugate base pairs in every acid base. There's a conjugate base pair, which is the acid conjugate base, and there's a conjugate pair of a base and conjugate acid. And that's the end of this lecture. So I'm going to end the PowerPoint. Let me end this slide. Actually, I'm going to stop the screen share. I'll end it right away. And I'm going to go back to the worksheet. Let's go through this worksheet pretty quickly. So you get it oriented here under the camera. That looks pretty good. I'm going to zoom in. Let's look at a few of these problems. This is just a one-page worksheet. Let's see, we'll get a nice pen here. So the first question says, decide which of the following are Bronsted acid-base pairs. And so at the top, an introduction tells you an acid-base pair can be an acid conjugate base, or it can be a base conjugate acid. So let's look at these. So number one, we have HF and F minus. Well, it looks like if HF loses the hydrogen ion, what's going to be left is the F minus. So this works. So HF and F minus is a conjugate acid base pair. How about this one, ClO3 minus and HClO3? Remember, the important thing that you're looking for is the one proton or one hydrogen transfer. So I've written that up here in the introduction. That's what's important. A one hydrogen transfer determines is the connection between a conjugate, an acid, or a conjugate pair. Let's look at the next one. So we have ClO3 minus, HClO3, sure, that works. If the ClO3 minus picks up in hydrogen, you get HClO3. So that's a one hydrogen transfer. How about the next one? H3O plus and OH minus. Well, if we do one hydrogen transfer from OH minus, we get O2 minus, so that doesn't work. If we do a one hydrogen transfer, say we added a hydrogen to OH minus, we get H2O. So the pair with OH minus, if we lost the hydrogen, would be O2 minus. If we gained a hydrogen, it would be H2O. But that doesn't work. Neither of those are present here. So you can also look at H3O plus. If we lose an H plus, we get H2O. That's not there either. So this is not a conjugate pair. I'll put a CP for a conjugate pair. Not conjugate pair. So I'm going to leave the other side for you to work out, okay? Problems 4, 5, and 6 are for you. And this is a worksheet I want you, no, I guess I don't want you to turn this one in, but I want you to do this side. You do this side. If you have any questions, let me know. This isn't too hard. You're looking for the transfer of a hydrogen ion. So let's look at the next set. And what I'll do is I will work on the left side, and I'll let you guys work on the right side. So predict either the conjugate acid or the conjugate base. So since HBr starts with an H, that's the acid. So let's remove that hydrogen ion, and then what's left over is a Br minus. So that's our conjugate base. So that's all you have to do. Just write the formula of what's missing, either the conjugate acid or the conjugate base. We have H2CO3 next. We'll take away one proton. What's left is HCO3 minus. So an important point, when you remove the H plus, you're going to have a Br minus if what you're starting with is neutral. So when you remove the H plus, you're going to decrease the charge by 1. So we start off neutral, we have to go down to a -1. When we're neutral, take away an H plus, HCO3 is a -1. Okay, here we have ClO4. We can't lose a proton because there's none there. So the only thing we can do is add one. So this is a base. Maybe I'll label these two. This is our acid. This is our conjugate base. I think it'd be helpful if you did that. This is an acid. That's a conjugate base. In this case, this is going to have to start off as a base. And we want to write the formula of the conjugate acid, which would be HClO4. And when we add an H plus, that we have to raise the charge by 1. So we go from a -1 up to 0. So we're HClO4 with no charge. Okay, so now we have HSO4. And the it's labeled already as a conjugate acid. So what we want to write down is the base. Remember, it's a conjugate. Let's see, this is the base, this is the conjugate acid. So if this is the conjugate acid, what we want to do is write the formula for the base. So what's the formula for the base? Well, the base was the substance that picked up, that accepted the proton. So in this case, the base is going to be SO4 2 minus. When it picks up a proton, it becomes HSO4 1 minus, -1. All right? So I'll leave the formulas 5, 6, 7, 8 for you to fill out. If you have any questions, be sure to drop in during office hours or send me an email or text. Okay, lastly, for each neutralization reaction below, link the conjugate acid-base pairs. So what's a neutralization reaction? We didn't mention that, but that's the reaction between an acid and a base is a neutralization reaction. So all of these reactions, the few reactions I showed on the PowerPoint were neutralization reactions. So it's between an acid and a base. It's an acid-base reaction. It's another name for neutralization. So I'll say acid base. Acid-base reaction is a neutralization reaction. So here we have nitric acid plus water is going to nitrate ion plus hydronium ion. So link the conjugate acid-base pairs. So we have HNO3 going to NO3 minus. So we have an acid here and the conjugate base here. And then we have H2O here going to H3O plus. This would be the conjugate acid, and this is the base. So remember, we label the species on the product side as the conjugates. the species on the reacting side, either an acid or a base. I'll leave the second one for you to do, all right? That's the one for you. So that's the end of lecture for chapter 14.1. So if you have any questions, let me know. And take care. I'll see you again next time.